Today I'm looking at the last section in Chapter 5. That's 5.6, Logistic Growth. Logistic growth is most commonly used in population growth models. Your population cannot continually grow exponentially. If you live in a town, you can't just keep expanding. At some point, you're going to run out of resources or you're going to run out of space. And in that case, the growth model is going to top off. Here's an example. Here you can see the graph starts at the origin 0, 0 and takes off with an exponential growth model where it is concave up in the initial stages until you get to the point of x1. And then it still increases, but it doesn't increase as fast. And it starts to hit a point where it slows down, and that's at the horizontal asymptote of the orange dotted line here. That entire graph is the graph of a logistic function. Please don't confuse this with a logarithmic function. Logistic and logarithmic are two different functions. Here's the formula for a logistic function. P equals f of t, and then you have L over top of 1 plus CE raised to the negative kt, where L, C, and K are your positive constants. Each of those variables, L, C, and K, well, I guess I shouldn't use the word variable because they don't vary, but each of those items are going to have a different impact on the curvature of the logistic function. Let me go through each of those properties. L was in the numerator of the formula, and that's where your horizontal asymptote is going to be. So whatever the number is for L, you could set y equal to L, and that would be the value of your horizontal asymptote. That's the upper bound. That's as high as that function is ever going to go. It's never going to get there, but it's going to have a ceiling where it gets really, really close. This is also known as the carrying capacity. How high can a function go? K affects the steepness of the curve, or how fast does that curve approach the asymptote. The slope at the largest point is going to occur at the inflection point. That's where I was changing over from concave up to concave down. That can be found by doing whatever L was and just dividing that by 2, because then you would be halfway to the carrying capacity. We call that the point of diminishing return. To the left of the point of diminishing return, or the inflection point, you approximately have exponential growth, and your growth rate is the letter K. Your textbook gets a little bit more advanced than what we need when we're talking about logistic growth. I'm going to keep it pretty basic with the following example and just kind of stick to this. So here I have the sales of an album. T is representing months from the time it was released, 0 through 7, and then P is representing the sales in thousands. I'm going to answer these 3 questions. First, I want to know where the concavity changes. So to answer that, I'm going to start by graphing. I put sales on the vertical, and then I'm going to put time in months on the horizontal. And I'm just going to try to approximate these points. So when I plot the points and connect them with the curve, you can see that the concavity probably changes right around here, approximately at t equals 5, where I have exponential growth, concave up, until I get to t equals 5, and then it turns concave down. I'm going to use the inflection point to estimate the max potential sales, L. Question B. As previously stated, the inflection point, P, is going to happen at L over 2. If I know the value at t equals 5 is 258, I can solve for the value of L. I write a simple equation, 258 equals L over 2. I'm going to cross multiply, and 2 times 258 would equal L. And here you can see that L is going to equal 516. So that's an estimation for the maximum potential sales, because once I got to T equals 5 of 258, I was halfway there. And now I see that these sales are probably going to top off approximately around 516, when in actuality, those sales were in thousands, so the sales are going to be at 516,000. So that's going to be the value for my horizontal asymptote, or my carrying capacity. Let's now take a second to let our calculator actually find the logistic regression and give me the entire equation for this curve in green. And then I can use that to estimate sales, and let's see how close our 516,000 max potential sales is compared to what the calculator says it would be. I'm going to begin by going to the lists in my calculator and entering in the months and sales. To get here, I went Stat, Edit, and then just started typing in the months in L1, 0 through 7, and then the sales in L2, 0.5 through 496. I'll give you a second to go ahead and do that on your own. At this point, you want to let the calculator come up with a logistic regression. To do that, I'm going to hit the Stat button. I'm going to go over to Calc for Calculate, and I'm going to scroll down to Logistic, not Logarithmic, Logistic. Hit Enter. The calculator will default to L1 and L2, so all I need to do here is hit Enter. And the calculator gives me the format. Now, the letters that they use, I had L divided by where the calculator says C. So they just use different letters than I did. Instead of L, C, and K, they're using A, B, and C. But everything's in the same spot. So the calculator tells me that C is 531.6, which we could probably round up to 532. C on the calculator is L in my formula. So the carrying capacity, according to the calculator, would be 532,000. Looking back at what we said before, we said we had a maximum potential sales of 516,000. The calculator estimates this a little bit better by getting a more accurate inflection point of 532,000. You could also graph this on the calculator. To graph, I'm going to hit second and then go to y equals. Or excuse me, it's just the same thing as hitting second stat plot. You're going to select the first graph, which is a scatter plot. You want your x data to come from L1, your y data to come from L2, and then you're probably going to want to adjust your window before you look at this graph. So I'm going to hit window. My x, I think from -5 will be good. We had out to 7 months. I'm going to stretch it out to 8. The y min, -5, should be okay. And our y max was 496. I'm going to stretch it out to 525. And then graph, and you can see this is the same thing essentially that I had when I did it by hand. If you'd like, you could go to y equals to type in the equation and come up with the regression for the logistic curve, and then you could predict what would happen at months 8, 9, 10, and so on. So artists and companies will use this concept for when they want to release a new album. They're going to let sales for the album increase as long as they can. And when things start to top off, they know it's time to go back in the studio and release something else. Apple does this exact same concept when they're releasing new phones. They put a new phone on the market and sales exponentially take off. But at some point they start slowing down and then everyone stops buying their phones. So then they release the next model and the exact same thing happens. Good companies know how to time this, so they know how to get the maximum amount of sales before they release the most current product. That pretty much wraps it up on logistic models. Like I said, there's more that you can do here, but we're going to kind of just keep it basic towards that. Just finding the equation and then predicting the maximum potential sales.